Now, let us talk about heat, and we showed you that work is a path function by taking different paths, and just now you have seen that depending on the number of steps you are getting different amount of work, right. So, it also indicates that or each process when you are taking one step is one path, taking 2 steps is another path, 3 steps another path, infinite steps another path. So, path meaning how you are going from P1 V1 to P2 V2, that is called path. Each path is giving you different values. So, work is a path function, you know, and heat is a path function also. Now, we are going to establish that why heat is a path function. Now, what is our understanding about heat? Our understanding about heat is that heat is something which is proportional to temperature. Now, how it can be a path function? It is a proportional to temperature, right, and also we have seen that it is proportional to mass, right, but there is another quantity that heat depends on, which is the specific heat, right, specific heat of a system, that for a unit mass system, for changing an unit amount of temperature, how much heat is required, and that specific heat varies from system to system. For water we take it to be 1. Now, it turns out for gases there is no single specific heat possible, depends how the process is carried out. Is it carried out by as a constant volume process or a constant pressure process? On that the specific heat will depend on. And first we are going to talk about the changes in as a constant volume process, right. So, again as I said, heat is specific heat and constant temperature. So, let us do that calculation. We know that du equal to dq plus dw. We will start from extremely basic thing, fundamental first law of thermodynamics. We always start from first law of thermodynamics in this kind of cases, right, so that we do not have to remember anything, always start from the beginning and then you can rearrange everything on your on the way. We are looking for heat. So, dq equal to du minus dw. By definition we can write that du plus p external dv, although I write just p, just take it to be p external. So, dq is p external dv. Now, what is du? Du, now you will see that what is the importance of exact differential. Du is an exact differential and u depends on both v and t. So, let us write that in terms of exact differential, del u by del v at a constant t dv plus del u by del t constant v dt. Okay. Now, this equation let us replace in equation 1 in equation 2. So, we write dq equal to del u by del v t dv. It is better to write p external here, so that we can understand that du. I am just replacing this du part by this thing, du by dt v dt plus p external dv. Now, put the two dv's together, du by dv t plus p external dv plus du by dt v dt. So, we got the expression of q. Right now, there is no assumption has been taken, we have expressed q in terms of this thing. Remember, we have taken this as a function of b and t, but we could have taken as p and t as well or p and v as well, it does not matter. You will see that for ease of our calculations, we adopt the variables that we require. Okay. So, now we are going to do an assumption, not assumption, but we are going to take a condition or a constraint. We say that the process is done at constant volume. Constant volume means what? That v has not changed. If v has not changed, what does it mean? dv is going to be 0. So, for constant volume, dv equal to 0. So, therefore, we get dq equal to del u by del t v dt, which gives us, oh, and we write V here just to denote that it is a constant volume change in the heat. So, now dq V by dt is equal to du dt V. Now, what is this du by dq by dt term? Can you tell me what is that? What it says? It says that what is the temperature, if I change the temperature, how much will be the change in the heat at a constant volume. You remember, heat is a function of three things like temperature, mass and specific heat, right. So, if you divide heat by temperature, what you are going to get? Mass and specific heat. For a fixed mass you get the specific heat. So, specific heat is defined by the fact that for an unit mass, how much change in the heat will happen given this much change in the temperature. And since this quantity is done at a fixed volume, we call that specific heat at a fixed volume, Cv. So, Cv is now defined to be du dt at a constant volume. What we write? That Cv, which is specific heat at a constant volume, is dq V by dt. This V is very important. This V denotes that we are talking about constant volume process. Never neglect those things. Equal to del u by del t at a constant V. That is our Cv, which means that if I now try to write it in a different way, then we can write, I can take that dt on this side and write that du at a constant V is Cv dt at a constant V, and this is true for all gases, not just ideal gas, it is true for all gases, and it is a very interesting important result, which means that if we know the specific heat of the system, we will be able to know the change in the internal energy if the process is done at a constant volume. Because internal energy is not something that can be measurable. We have to understand what is measurable and what is not measurable. And remember again that all those definitions of heat, work, everything has stemmed from somewhere. We first understood what is temperature by associating that to a physically measurable quantity of gas systems, PV. That gives us a sense of temperature or definition of temperature. From temperature we got the definition of heat, right. So, and now from heat we are getting a definition of internal energy or change in the internal energy, right. So, we have started from somewhere and we are going to get all the relevant quantities. We will not be able to measure this du directly, we can do that in computationally, but not experimentally. But a measurement of this, measurement of heat at a constant volume will help us to calculate the Cv, and therefore, will help us also to calculate the internal energy of the system, right. And that is what is so important about this particular equation. Okay. Now, let us go back and see what I have here. I have that, I have discussed this, and I have discussed this one, and I have discussed this one. Okay. Now, I have discussed also this particular quantity here Cv, and this particular quantity also I have talked about, that you can get the change in the internal energy by integrating the Cv dt. Now, when I do that, when I do this particular integration, the Cv may or may not be dependent on temperature, right. Because see, it is within the integration, this particular Cv is inside the integration, it may or may not be dependent on the temperature. But it turns out that for a region of our interest, when you are changing the temperature from T1 to T2, in that region Cv may not vary much with the temperature, and in that case we can always take out the Cv outside the integration and we will get change in the internal energy as Cv T2 minus T1. The ideal gas system that we are going to talk about does not depend on temperature, okay, and that we can very easily see. So, for example, we know that U equal to 3 by 2 RT, So, du by dt at a constant volume is going to be 3 by 2 r for ideal monoatomic particle, not for any other thing, monoatomic particle. One particle ideal gas has 3 by 2 RT energy, 1 mole of gas, and Cv therefore is 3 by 2 R, which does not depend on temperature. In that case, our internal energy we can write like this, and I have already discussed about this particular thing. And this is a typical graph showing how Cv varies with temperature. So, essentially we are saying that we are taking some midpoint, some this value in the midpoint somewhere for our Cv. Of course, it will not be exactly accurate, but it all depends on how much accuracy you want in our calculations, and that is where the error bars and everything come in the picture. Nothing is accurate, like it depends on how many decimal places you want the result to be correct. Right. Now, we are going to talk about change in the change in a constant pressure, du equal to dq plus dw, and write dq equal to and write du equal to du minus dw, and then we can say that there is a change in the internal energy, right. So, let us say the change is happening between two states 1 and 2, we are going from 1 to 2, and the internal energy at the position 1 is u1, and let us say internal energy at the position 2 is u2. So, du, so we can say so this is an infinitesimal change, right. Let us say we talk about a definite amount of change. So, there is a difference between when we write d versus del. So, when you write del, it signifies we are talking between final and initial one. For example, del u is u2 minus u1. However, du when we write, we are talking about an arbitrary infinitesimal change. That is the notation that we are going to use in thermodynamics. So, when it is q, so let us say q equal to delta u minus dw means plus p external delta v. You see, can I write like that? I can write like that only when, yes, why you are not? So, we are taking q to be a change in heat. Q is the amount of heat that is required to be input or output. So, that is a change. This is a change, but is this part correct? What was the definition of work? Integration P external dV. So, this part is not correct. Actually, what I should have done is that I will tell you, I should have written this way. Going from that step to next step, I should have done this, integration of dq equal to integration of du minus integration of dw, correct? That should have been the case, going from 1 to 2, 1 to 2, 1 to 2. Now, I am saying that 1 to 2 is just a q. This one is delta u that I have defined to be u2 minus u1. Now, in this case, I should write p external dv integration 1 to 2, up to that is fine. But then the next step, when I write q to be delta u plus p external dv, I am assuming p external to be constant. So, therefore, I have to put p here, and then I can write that. You see, it is a very small difference, but the earlier one was not correct, now it is correct, because we are assuming the process is done all along at a constant pressure. For example, if you do a PV diagram, let us say this is P and V, you are doing a PV diagram, you are going exactly that way, then it is correct. So, now integration of V from 1 to 2 is nothing but V2 minus V1. So, it is U2 minus U1 plus P external V2 minus V1 equal to QP. Now, I will simplify it again, U2 plus P external V 2 minus U 1 plus P external V 1. Is it okay? I have just put U and V P V together. I have just put. Okay. Is this last line fine? Now I define a new quantity H to be U plus P V, such that my H 1 is U 1 plus P V 1 and H 2 is U 2 plus or P 1 V 1, you can say P 2 V 2. Now, P remaining constant I can write as P. Okay. Once I do that, I can write Q P as H 2 minus H 1. Okay. So, what did I get? That heat at a constant pressure is change in a quantity which we call as enthalpy. So, change in heat at a constant pressure is nothing but change in enthalpy. Enthalpy is our own definition. We define that and we define that to be U plus P V. So, I will clear it and write once more. So, Q P we got to be H 2 minus H 1. So, in that case d Q P is nothing but d H, and you will see later on that it is a quantity that has natural variable of P and T. It is easy to express this quantity in terms of P and T, just like it is easy to express U in terms of V and T. Okay. So, this is our new quantity. Now, specific heat at a constant pressure will be the same thing dq. By the way, I should not cut the d. So, by notation the d is cut to denote that it is a path function, but once I have specified whether the process is done at a constant pressure or constant volume, it is no longer path function. So, you see q is a path function because q can be changed by either constant pressure process or constant volume process. But if I already specify the process is done at a constant pressure and say Q P, then it is no longer path function. I have two different ways to go somewhere and each are different of different lengths. However, if I say that okay, I have to go only that way, then it is no longer different. So, therefore, Q P is no longer a path function, Q P is a state function and so does H. H is also a state function. Okay. So, now coming back to that same thing, I will just write it below. C P is d Q P. So, therefore, I should not cut it, that is where it come from, I should not cut the d. So, C P is d Q by T, which is nothing but del H by del T at a constant pressure. It is clear? So, what we got? C V we got as del U by del T at a constant V, and C P we got as del H by del T at a constant P. Do not write del U by del T at a constant P for C V, because it will be different and not the other way around, and do not think that del U by del T at a constant P will give you C P, that is also not going to give you. You have seen that by derivation that it is like this. One is del H by del T at a constant P, another is del U by del T at a constant V, and these two quantities are different, and therefore, C P is not equal to C V, and since they are not equal to, then Q P and Q V they are also different, and therefore, heat is a path function. Okay. So, I think I have done all that here. I am just going over because I have done that. Yeah. So, we have said that heat absorbed in a process at a constant pressure is equal to the change in enthalpy. dH is an exact differential because dQp is exact, we have discussed that. Pressure and temperature are natural variable of enthalpy, just to tell you that we are going to use that later on. And so, now we can see that this part I can just show you. So, since pressure and temperature are natural variables, we can express the differential amount of H in terms of these two quantities. Okay. So, we have seen that Cp is Qp by dQp by dt, which is del H by del T at a constant pressure, that we know. And I said that H natural variable of H is P and T. Whenever that happens, you can always write that in terms of these two variables. You will write it so many times that will become extremely easy. Okay. Now, we know that we want to talk about constant pressure process. So, therefore, this quantity is going to go to 0. So, del H P will be del H by del T at a constant pressure dt. I do not know what we are going to get from that, just one second. Yep. Okay, I understand my argument. I will do that once more. So, H has a natural variable of P and T. So, therefore, we can write dH as del H by del P T dP plus del H by del T P dt. Now, at a constant pressure, dP equal to 0, and therefore, dHP is nothing but del H by del T P dt. Now, we know that Qp specific heat is del H by del T P, right. So, therefore, we can write that del H P is Cp dt. So, if you have to calculate the change in enthalpy for a constant pressure process, we can calculate that, right, or we can also calculate the change in enthalpy by assuming Cp to be independent of temperature. We can express that change in the enthalpy as Cp T2 minus T1. What do we have done? We have just integrated on both sides and assuming Cp is constant, assuming it to be a constant. Okay. I think that is what is done here. Yep. And we can get also the by integrating we can get the heat. Now, this is the last part of today's lecture, that we can show that Cp is always greater than Cv. Now, how do we do that? So, that is the question. So, that is a very nice derivation that we are going to do. So, Cp by definition is del H by del T at a constant pressure, and what is Cv? Del U by del T at a constant volume. Now, let us start with Cp. Now, we know that H is U plus Pv, right. So, let us call it equation 1, equation 2 and equation 3. So, then integrating both sides of equation 3 with T, we are going to get del H by del T at a constant pressure is equal to del U by del T at a constant pressure plus, since P is constant, because we are doing at a constant pressure, we do not have to do that product differentiation. We can just take P common out and we are going to get del V by del T at a constant pressure. Okay. This is fine, this step. Now, you see we have del U by del T at a constant pressure. We know that we cannot write that as a Cv, because our Cv is del U by del T at a constant volume, but here we get constant pressure. So, we cannot just substitute that. So, what we are going to do is that we are going to, that is a little bit lengthy process, we have to again express u in terms of v and t. So, del u by del v t dv plus del u by del t v dt. And this next step is very important, and listen carefully. This I had several times problems when I was studying myself. See, I have this quantity del u by del v t and del u by del t at a constant volume. I want to get to del u by del t at a constant pressure. I have this, I have this, I have this, I want to get to this. How do I get? That is what we are trying to do right now. I have this, but I want to get to this. If I have to get to this, I have to take a derivative of u with t at a constant pressure. I have to do that. Right now I do not have that. Right now what I have is this one. So, what we have done is that we have expressed the total differential of u, which I can always write like that. Now, I can take a derivative of this particular thing with respect to t at a constant pressure. So, doing that I am going to get del u by del t at a constant pressure, right. I am doing the derivative now of this particular equation, equation number 4. I am doing the derivative on both sides of equation number 4 with respect to temperature, keeping pressure constant. What will be the right hand side? Now, the most problematic part is the right hand side. Should we take a product or should we not take a product? Like, should we do as a product of these two things or not? Now, in order for you to understand that, I would like to tell you that this is where the problem sometimes come. This du is a differential amount. So, when I say that I am taking a derivative with respect to a particular quantity, what essentially I am doing is that I am dividing by dt at a constant pressure and taking the limit of temperature to 0. So, essentially I am dividing by delta t. So, if I divide this particular quantity by delta t, this quantity is not going to change, because there is a dt is going to come. Okay, if you want, I can do it into one more step. Okay, let me write it here. Du is del du by dt constant volume plus del u by del t del v dv. Okay, this is what we have. What we are doing is that divide both sides by, in fact, imagine that it is not du, imagine it is del u. First principle, both sides by del t. What are you going to get? Del u by del t, but at a constant pressure. So, since I am dividing, this quantity is not going to change, del t by del t plus del v by del t. Okay. But the change is such a way that I am doing that at a constant pressure. Take delta t tends to 0. What I am going to get now? Is it clear? So, you see these quantities, I am not taking this particular quantity, I am not taking a derivative again. I am not taking the derivative of this quantity and this quantity. Essentially, when I am saying I am taking a derivative, it essentially means that I am changing this, already the differential amount of the numerator is already there. I am dividing by a differential amount of the denominator, which is delta t, and that gives me a derivative of this quantity. This goes to 1 and this giving me a derivative del v by del t at a p. Okay. Is it clear? If this is clear, then you will have no problem in future of taking these partial derivatives. If you have difficulty, always go back to the first principle, and that is why when we talked about partial derivative last class, we talked about how we are getting that partial derivatives. Remember, we did it from first principle by changing the differential amount, and we discussed about what partial derivative means, that pressure remains constant, volume changes when you are talking about at a constant pressure partial derivatives. So, essentially when you are talking about a partial derivatives, we are going to the first principle of changing some amount infinitesimal amount of a particular quantity and looking at how the other quantities changes, and that is what we are doing it here. So, now I will write it here again, del u by del t at a p is del u by del v t del v by del t p plus del u by del t v, because dt by dt will cancel, meaning giving 1, okay, even if it is a constant pressure, because it is going to be 1. So, now I am going to I have to replace this equation number 5 in my equation number 6, meaning I have to replace this du by dt p by this whole quantity, and the space is little bit less. So, I will just try to write once more here, del h by del t at a constant pressure is therefore del u by del v at a constant temperature del v by del t at a constant pressure plus del u by del t at a constant volume. You see, interestingly, when I change this variable, just the p, then it is so different compared to when it was del u by del t v. Del u by del t at a constant v is very different from del u by del t at a constant p. So, I am changing the temperature and looking at how the internal energy changes. If that is done at a constant volume versus at constant pressure, is entirely different process. That is what it is denoted by these subscripts. So, that therefore, the subscripts are essential, extremely important, do not neglect that. Okay. So, now, so this is now I have substituted that del u by del t p I have substituted, then I am going to write this particular term that is left out, del v by del t at a constant pressure. I am trying to erase this part. Okay. Now, what is this particular quantity? Del u by del v t, is it familiar, del u by del v t? No. Del v by del t p, no, but is it something is common? Yes, del v by del t p is common thing from these two equations. So, I am going to take that, del v by del t p is common, which is giving me del u by del v t plus p plus du by dt v. What is this quantity? Cv, and del h by del t p is what is that quantity? Cp. So, I have got, now I am going to erase the top part. Okay. So, we got that Cp minus Cv therefore, is this particular big quantity, which is del v by del t p del u by del v t plus p, that is it. Yeah. Now, we have to see what each of these quantities is. What is del u by del v t? What does it say? Del u by del v t, says that if I change my volume at a constant temperature, whether internal energy is going to change or not. Now, can you tell me whether it is going to change or not for ideal gas? For ideal gas, it is not going to change. Why? Because u does not depend on v, whether the v is small or v is big does not matter, it is always depends on temperature only. If temperature is constant, then it is not going to change even if you change the volume. However, it is not true for real gases, remember, because real gas has attraction. So, when you change the v, the particles get separated from each other and energy is going to increase actually if they are coming from stable states. It depends on where you start. So, this quantity is going to be 0 for ideal gas. So, then we land up with del v by del t p into p, because this quantity is 0. And what is del v by del t p? So, you have to go back to P v equal to nRT. So, let us so P v equal to nRT, and it is a constant pressure differentiation. So, P is a constant. So, let us differentiate with respect to T on both sides. So, P del v del T at a constant P is going to be nR. So, del V by del T is nR by P. So, let us write that nR by P into P is equal to nR. So, Cp bar, which is heat capacity at a constant pressure for 1 mole, minus Cv bar, the same thing at a constant volume, is equal to R for ideal gas alone. By the end of the class, we are going to do it in general. That means, irrespective of whether it is ideal gas or not, and you will see this quantity is going to be much more complicated. It will be T V alpha square by kappa T. We have not defined any of this. So, right now you do not worry about it, but you are going to have a very general expressions of Cp minus Cv. But for ideal gas, Cp is minus Cv is R, and that means, and since R is positive quantity, we can say that Cp is greater than Cv. Now, mathematically it is easy to understand like that it is greater than Cv, but physically can you explain why Cp is greater than Cv? This is one of the very important questions in thermodynamics, that why Cp is greater than Cv. Cp is when you change your when you give heat at a constant pressure, and Cv when you give heat at a constant volume. So, if you do at a constant volume, what happens is that there is no work done. So, whatever heat you are getting, putting in is going there, right, as to change the internal energy. So, however, for Cp, in order to, so when you heat at a constant pressure, what is happening? Your volume is also changing. So, the amount of heat is going in two ways: to change the volume, that means to do the work, and then whatever the rest is there, that is going to change the heat. So, you have to put more heat in order to change the same amount of temperature. So, Cp is that you need more heat to change the same amount of temperature in case when there is a constant pressure, because some amount of heat is going into work. But in the Cv case, since the volume is same, nothing is going to work. So, everything is going to change the heat, and that is the reason Cp is greater than that Cv always, irrespective of whether it is a real gas or ideal gas, but the amount will depend on what system we are considering. Okay. So, we will end today here.